This call is now being recorded.
Good afternoon, everybody. In last lecture, we have seen numerical on the Francis turbine. Okay. Now, in this lecture, we have to start our new point, that is regarding the draft tube. Now, what is the draft tube? The draft tube is a pipe of gradually increasing area which connects the outlet of the runner to the tail race. Okay. It is used for the discharging water from exit of the turbine to the tail race. This pipe of gradually increasing area is called as draft tube. Now, one end of the draft tube is connected to the outlet of the runner, while the other end is submerged below the level of the water in the tail race. Okay. The draft tube, in addition to serve a passage for water discharge. Now, what is the uses or advantages of the draft tube? When we attach a draft tube, at that time what happens? The net head on the turbine increases and turbine develops more power, and also the efficiency of the turbine increases. If a reaction turbine is not fitted with a draft tube, the pressure at the outlet of the runner will be equal to the atmospheric pressure. Okay. And the net head on the turbine will be less than that of the reaction turbine fitted with a draft tube. Also, without a draft tube, the kinetic energy, that is V2 square divided by 2G, rejected at the outlet of the runner, will go to the west to the tail race. This was the introduction regarding the draft tube. Okay. Now, what are the types of the draft tube? The draft tube types are, first type is the conical draft tube. This is the second type, that is simple elbow tube. Now, this is the third type of draft tube, that is moody spreading tube. And this is the fourth type of draft tube, that is draft tube with circular inlet and rectangular outlet. Okay. These are the four types of your draft tube. The conical draft tube and moody spreading draft tubes are more efficient, while the simple elbow tubes and the elbow draft tube with circular as compared to the other types of the draft tubes. Now, we will start our next point. That is the draft tube theory. So, what we have to prove in this draft tube theory? We have to prove in this draft tube theory that pressure at the inlet of the draft tube is less than the atmospheric pressure. Okay. This is the turbine casing. This is the tail race. This is the outlet of the draft tube. This is the inlet of the draft tube. This is the distance Hs, that is vertical height of the draft tube above the tail race. Then Y is the distance of the bottom of the draft tube from the tail race. This is the Hs distance and this is the Y distance. Now we have to apply Bernoulli's equation to the inlet, that is section 11, and to the outlet, that is section 22 of the draft tube, and taking this section 22 as the datum line. Okay. What is Bernoulli's equation? In Bernoulli's equation, we consider three terms, that is pressure head, velocity head, and the datum head. Now applying the Bernoulli's equation to the section 11 and section 22, we will get, first we will apply Bernoulli's equation to the inlet of the draft tube, that is P1 by rho g, then plus V1 square by 2g plus Hs plus Y, that is equal to applying Bernoulli's equation to the outlet of the draft tube, that is P2 by rho g plus V2 square by 2g plus 0 plus HF. Now what is this HF? HF is equal to loss of the energy between the section 11 and 22. Okay, HF is the loss of the energy between the section 11 and 22. Now pressure head at the outlet, that is P2 by rho g, is equal to atmospheric pressure head plus Y. Okay, now atmospheric pressure head is PA by rho g plus Y. P2 divided by rho g is equal to PA by rho g plus Y. Now equating two equations, P1 by rho g plus V1 square by 2g plus Hs plus Y is equal to PA by rho g plus Y plus V2 square by 2g plus HF. Cancelling the common term, that is Y, we will write it as the equation as below. P1 by rho g plus V1 square by 2g plus Hs is equal to cancelling Y, PA by rho g plus V2 square by 2g plus HF. Okay, now I want P1 by rho g, that is atmospheric pressure, on one side. Okay, therefore I have written P1 by rho g is equal to PA by rho g plus V2 square by 2g plus HF minus V1 square by 2g minus HS. Okay, now rearranging the term, we will get one equation, that is P1 by rho g is equal to PA by rho g minus HS minus into bracket V1 square by 2g minus V2 square by 2g minus HF. Hence here we have proved that pressure at the inlet of subtracting these all terms from the atmospheric pressure. That's why it is proved that pressure at the inlet of the draft tube is less than the atmospheric pressure. Okay, please write down the equation. Now the next part. Write down the final equation by rearranging the term. We will get pressure at the inlet of the draft tube is less than the atmospheric pressure. Now we will start our next point, that is efficiency of draft tube. What is the definition for the efficiency of draft tube? The efficiency of draft tube is defined as ratio of actual conversion of kinetic head into pressure head in the draft tube to the kinetic head at the inlet of the draft tube. Therefore, it is mathematically written as draft tube efficiency is equal to actual conversion of kinetic head into pressure head divided by kinetic head at inlet of the draft tube. Okay. Let V1 is equal to velocity of water at the inlet of the draft tube. Then V2, velocity of the water at the outlet of the draft tube, and HF is equal to loss of the head in the draft tube. Therefore, theoretical conversion of kinetic head into the pressure head in the draft tube is equal to V1 square by 2G minus V2 square divided by 2G. This is the theoretical conversion of kinetic head into the pressure head in the draft tube. Now, what is the actual conversion of kinetic head into pressure head? That is V1 square divided by 2G minus V2 square divided by 2G minus HF. This is the actual conversion of kinetic head into pressure head. Now, we will write down draft tube efficiency formula. Efficiency of draft tube is equal to V1 square divided by 2G minus V2 square divided by 2G minus HF divided by V1 square divided by 2G. So this is the formula for draft tube efficiency. Now we will solve one numerical based on the draft tube. We will solve one numerical based on the draft tube. Please write down conical draft tube having diameter at the top as 2.0 meter. Pressure head at 7 meter of water. Discharges water at the outlet with a velocity of 1.2 meter per second at the rate of 25 meter cube per second. If atmospheric pressure head is 10.3 of the water and losses between inlet and outlet of the draft tubes are negligible, find the length of the draft tube immersed in the water. The total length of the tube is 5 meters. This is your section number 11, section 22. This is Telres. This distance is y. This distance is hs. Velocity is v1. Pressure is p1 at the inlet. v2 they have given us as 1.2 meter per second. Okay. Now, what is our first step to solve the numerical? First, we have to write down all the given data. Diameter at the top, D1 is equal to 2.0 meter. Pressure head, P1 by rho G, is equal to 7 meter, and they have given that is vacuum pressure. We have to convert that into absolute. Therefore, we will subtract it from 10.3 minus 7.0, that is equal to 3.3 meter, and that is the absolute. Now, velocity at the outlet is equal to 1.2 meter per second. Discharge is equal to 25 meter cube per second, and HF, that is head loss, they have given as negligible. They have given it as negligible. Okay. Let the length of the tube immersed in the water, we consider it as y meter. We consider it as y meter. Total length of tube. Total length of tube is equal to 5 meter. 5 meter. The velocity at inlet V1 is equal to discharge divided by that is equal to Q divided by pi by 4 D1 square. Putting the values, we will get Q value is 25, pi by 4, D1 is given as 2, that is square. Calculate this value. Yes, this value is equal to 7.957 meter per second. Now we have to apply one equation here. We have to apply one equation here. P1 by rho G is equal to PA by rho G minus HS minus V1 square by 2G minus V2 square by 2G minus HF. Putting the values, we will get 3.30 is equal to 10.3 minus HS minus 7.957 square divided by 2 into 9.81 minus V2 is 1.2. 1.2 square minus 2 into 9.81 and HF is negligible. That's why we have to write it as 0. Now here the unknown quantity is HS. Please calculate the value of the HS. Yes, the value of HS is equal to 3.8464 meter. Now, what we have to calculate? We have to find out length of the drop tube immersed in the water, and total length of the tube is given as 5 meter. Therefore, Y is equal to total length minus HS. Total length is given as 5 minus 3.8464. The answer is 1.1536 meter. Means the length of the draft tube immersed in the water is equal to 1.1536 meter. Now, what is our next summary? The length of the draft tube immersed in water, that is Y is equal to 1.1536 meter, and this is our answer. This is our answer. Please complete the numerical. To summarize the lecture, first we have seen the basic about the draft tube. Then we have seen types of draft tube, that is conical draft tube, simple elbow draft tube, moody spreading draft tube, and draft tube with circular inlet and the rectangular outlet. Then we have seen draft tube theory. In that, we have proved that pressure at the inlet of the Then we have seen the formula for the efficiency of the draft tube. This is the formula for efficiency of the draft tube. And at last, we have seen one example on the draft tube. Okay. So here we will end our lecture. Thank you. Have a good day.
Ma'am, attendance